it's my pleasure to introduce Dr. Jim Bellingham. Jim just drove in from the Cape, and apparently what is typically perhaps an hour and a half to 2 hour drive took an excess of 3+. And I can't say where the traffic was. Jim said it started at Woods Hole's parking lot. So apparently never improved. So a few words about Jim. Dr. Jim Bellingham is appointed to Woods Hole's Oceanographic Institution as the first director for the Center for Marine Robotics. Jim was co-founder of Bluefin Robotics, Massachusetts-based company that develops, builds, operates autonomous underwater vehicles. He came to Woods Hole from Monterey Bay Aquarium Research Institute, where he was director of engineering and most recently chief technologist. Dr. Bellingham is author of dozens of scholarly papers, has participated in research expeditions around the world, from Monterey Bay to the Mediterranean Sea to the Antarctic, and has served on numerous scientific advisory boards and steering committees, including chairing the Naval Research Advisory Committee and serving on 4 National Academy studies. Jim earned his SM/SB physics degrees from the Massachusetts Institute of Technology. He also earned his PhD degree from the Massachusetts Institute of Technology, where he was founder and manager of the Autonomous Underwater Vehicle Laboratory. The research and experimentation that continues to be conducted only further extend the Institute's impressive and long-standing legacy as the intellectual engine behind countless discoveries and innovation in undersea decades. So please join me in welcoming Jim Bellingham from the Woods Hole Oceanographic Institute.
Well, let me tell you, am I ever glad to be here? So, not where I was just a few minutes ago. So it's a pleasure. It was a great honor to be invited to come talk to you. I hope you managed to get a second drink, maybe even a third in there, and we'll have a good conversation, I think, about marine robotics, and I think it's a particularly apt topic for this particular region, for both historical reasons and I think also for future reasons. You know, the historical reasons are, as I usually say when I'm giving a talk to my fellow New Englanders, we are a maritime region. This part of the country, well, maybe folks came across here thinking that they were going to make their make their living farming, but very quickly they learned that it was going to be necessary to fish as well and develop a trade industry also. And so we all know that New England actually has a proud history of shipbuilding, ship racing, trade, fisheries. Some of the finest sailing vessels in the world were built in this part of the world. I have to note that they were owned by New Yorkers, but nonetheless, they were built in New England. A transition to steam began to occur up in Quincy, actually started by none other than Watson, who was Alexander Graham Bell's assistant. He took his money and invested it in a shipyard. And of course, during World War II, some of the largest shipyards in the country were out in this part of the world. You know, the shipbuilding business has fallen on lean times. There's no question that if you look across to Asia and you look at booming commercial shipyards there, we don't, we're not really players in that particular domain. We build military ships, but the larger commercial businesses have moved overseas. But I think it's interesting to note that there are new industries here, and the new industries are in high tech, and they're in an intersection of high tech and our traditional maritime environment. Marine robotics is certainly a central piece of it, but marine robotics marine robot doesn't go very far unless it has the energy systems, unless it has the sensors on board, unless it has the software. And in fact, we're building a whole industry out here, motivated, as was the original shipbuilding, partly by commerce, partly by defense, and this time largely being led by folks who are struggling to understand the ocean environment. So of course today in the oceanographic world we still tend to explore the ocean on ships. This could easily be today at Woods Hole, although I will say there were no ships at the dock when I left. You know, pretty much every week there's a loading exercise down there as a group of scientists haul their gear on board, install it, set up in the science labs, and then head out to some remote part of the world, out to the North Atlantic perhaps, maybe further. Alvin was on shore for a brief period. Alvin, the human-occupied vehicle, was on shore for a brief period about a month ago, and that's pretty unusual. She spends most of the year at sea. Now, of course, the problem is that there's a lot of parts of the world that actually are, well, they're difficult to get to with ships. And of course, the primary way of introducing instruments to the ocean from a ship is to lower it from a wire. And in fact, when you're in the ice, wires tend to be a pretty hazardous proposition. They get broken by the ice, particularly when the wind conditions are large. And these are pictures of an autonomous underwater vehicle built at Woods Hole by Hanumat Singh. This particular vehicle was deployed, in fact, to do a very simple mission, which is to measure the thickness or map the thickness of the underside of the ice. And in fact, this is in Antarctica. This mission was launched from an Australian ship, and there was a group of people running around on the surface drilling holes. And I like to say that when they got together and they compared the truth, which is the human people drilling holes on the ice, with the robot results, what they found was the robot, in fact, measured a slightly thicker ice sheet. And after some thought, the scientists decided the robot was probably right, because after all, the people probably were choosing the thinner places to drill. So when our robots get smarter, they'll figure that trick out too. But for the moment, they're a pretty unbiased observer of the ocean environment. Now, the thing is that these robots, not so long ago, when I started out building robots for the ocean sciences community, it was in the late 80s, and they were really curiosities. So the first vehicle I built was called Sea Squirt. It weighed, I don't know, about 80 pounds. It had a bunch of instruments on it, which were pretty lousy instruments. I mean, you wouldn't have really trusted the data off of it. The vehicle could run for about 2 hours, about at a knot. So you can imagine it didn't really cover very much. I used it mostly in the Charles River for developing software. You fast forward to today, and we have a host of different types of vehicles. We have propeller-driven vehicles which can run up to 3 weeks and cover distances of up to 2,000 kilometers. They carry extremely sophisticated instruments like a genomic package called the environmental sample processor, which literally extracts microorganisms from the seawater, breaks them open, extracts their DNA, and it detects the individual DNA, looks for particular DNA sequences so as to actually, in effect, do a molecular fingerprint of the organisms in the ocean. So we've come a long way. In not really very long, in sort of 20, 25 years in the ocean sciences. And today, actually the glider vehicle, so this picture has a propeller vehicle shown with a stream of bubbles behind it, which of course you all know. People in this room, I'm sure there's people in this room with experience with torpedoes. You know, cavitation is not a good thing, and in a lightly loaded AUV doing 3 knots, cavitation is quite a trick. So no cavitation there. Now the vehicles behind it are these glider vehicles, and those are the very long endurance platforms that we tend to use in the ocean sciences. They carry very low power payloads and therefore are a good match for missions where you aren't going to run fast. Those things maybe weigh, sort of like the old Sea Squirt, maybe 80 pounds or something like that. 120 pounds maybe, but they can last for months. They can last for 3 months to some of the longer endurance ones last a year in the ocean, traveling about a half a knot. And it's pretty unusual these days for physical oceanographers to go to sea and not take a bunch of these systems with them for characterizing the ocean environment. Now, what does the future look like? Well, you know, one thing for sure is that if you look at the history of robotics in the ocean environment, we do have some indications that there are big jumps. And so here you have some remotely operated vehicles. In that upper left-hand corner is the Jason vehicle, which was built at Woods Hole. And by the way, I trace Woods Hole's robotics really back to one person, and that's Bob Ballard. So when when Bob Ballard stopped working with Alvin, he decided he was going to build teleoperated systems. He started the Deep Submergence Lab, and he recruited a bunch of smart people. And they built him Jason, actually the original Jason. Jason 1, the vehicle before this. And after they were done doing that, they went on, built on all kinds of other types of robots. They built the autonomous benthic explorer. A group of them separated and created a new lab where they built the Remus vehicle. So I do give Bob an enormous amount of credit, in effect, for setting Woods Hole on what has been a tremendously scientifically productive track. Now, you know, back in the 90s, there were not a lot of organizations that could build a deep diving, remotely operated vehicle that could, you know, something that could go to 6,000 meters. Woods Hole was one of few. But today, you know, you come forward to 2016, and literally one company alone, Oceaneering, probably operates something on the order of 300 multi-thousand-dollar vehicles. And that's, of course, because if you look at oil and gas, deepwater oil and gas fundamentally depends on these platforms as their eyes, as their hands, in order to do the site surveys, in order to do the installation, in order to do the inspection and maintenance, and ultimately the decommissioning of all of that incredible hardware that's being put on the seafloor. So we do have an indication of where a technology can go in the ocean environment when you suddenly have, in effect, a market pull. Now, the autonomous systems, I think, are sort of at that cusp. Right? They haven't really reached that enormous level of adoption. They're used, that's for sure, but they're not adopted in the same numbers or to quite the same impact as the ROVs are at this point. And within Woods Hole, you have two groups. That one down there at the lower right, the Deep Submergence Lab, of course, that's the lab that was founded by Bob Ballard. And they have a long history of doing things like finding the Titanic, the Bismarck. They actually get very upset if people start thinking they're a shipwreck hunting lab. They're not. They do an enormous amount of work for scientists, mostly in mid-ocean ridges, occasionally in the Arctic. They did survey the Deepwater Horizon incident with the Sentry vehicle. Turned out to be a very important set of measurements that helped them understand the dispersal of the deep plume from that spill. And they have a long history of building vehicles. This is a lab that's filled with a fair number of PhDs who love a challenge and like doing sort of one-off type systems that then get emulated and used elsewhere. Now, the Oceanographic Systems Lab is really known these days largely for their Remus vehicles, and they built a lot of different vehicles. They built actually the cabled observatory off of Martha's Vineyard. They built a set of towed systems, the Foss towed system back in the day, but pretty much everyone knows them as the Remus Lab, and it all started with the Remus 100, which is that little vehicle there in front, kind of human portable. And then behind it, all the way at the back, is the Remus 6000. The number refers to the depth rating. So the Remus 6000, for example, this group used to find the Air France airliner that went down in the mid-Atlantic. They actually used 3 vehicles, running 3 of these vehicles simultaneously from a ship. Coverage rate, roughly linear coverage rate of about 10 knots. So that compares to about a knot and a half with deep tow. So they were getting tremendous coverage rates there. Actually, it was the 4th survey and the 2nd with this group where they found that. So this group here has built a large number of vehicles, and of course they spun out Hydroid. And I think this is another place where I should say that Woods Hole is actually incredibly lucky to be where it is, because we are in the midst of a set of other organizations that allow us to specialize on our particular activity, because there's other people who can do the heavy lifting in other domains. And I'll give you an example of that. The Remus group does an awful lot of work with the Navy. Now, when you put a vehicle on a Navy platform, there's an awful lot of modifications that might be necessary in order to do that. And I can tell you that our engineers, they're great, they're really good AUV engineers, but we're not specialists in the design of submarines or naval surface vessels. And so as a consequence, almost all of that work is done in collaboration with the Naval Undersea Warfare Center. And so I think that's part of what allows the Woods Hole folks to remain fairly lean. And of course, now you look at the big big primes in the area and the companies. You know, again, Woods Hole will build onesie-twosies, but when the Navy says, well, we're really interested in buying 100 of these, we're not going to build 100. And that's where we end up licensing these out to the local high-tech community to build. And Hydroid is one example of that. Actually, the optical comms is another example, and there's a series of things. And of course, MIT. We have a joint program with MIT. I spent 20 years there, so I have strong roots in that organization. But they work sort of the very low end of the TRL scale, and they, for us, make tremendous partners because they're always trying crazy things, of which some might actually work. And when they look promising, we get a chance to stick them on our underwater vehicles. Now, I think that, you know, compared to where I was when I first started these vehicles, I assumed when they went underwater, you didn't get to talk to them until you got them back. But these days, there's increasing underwater communication capabilities that are available that let you begin to kind of blur the lines, if you will, between autonomous underwater vehicles and ROVs. And so you can see here, you know, 3 different examples, and these are by no means exhaustive. They happen to be the methods that we tend to be pursuing at Woods Hole. Acoustics, of course, and you can get long range. You probably can't see that graph, but it shows kilometers on the x-axis there, so that's out, I think, 75 kilometers, and in depth, in thousands of meters. And what you're seeing there is the transmission intensity of sound from a source there at the upper left. And the point there is something that, again, in the defense community, we understand very well, is sound doesn't propagate straight lines in the ocean. There's shadow zones. There's regions where the sound intensifies. And you have to understand these in order to communicate. So acoustic communication is not just signal processing. It also involves an intimate understanding and exploitation of the environment. Free space optics is kind of a newer capability, and of course the great thing there is latencies effectively go away. I mean, compared to acoustics, they're basically zero. Compared for other things, they do ultimately limit your communications rate, and you can push very large amounts of data through the ocean at ranges of 100 meters. Now, 100 meters doesn't sound like a lot, but it turns out being able to push 1 to 10 megabit a second across 100 meters in the deep ocean, which Norm Farr, who does the free space optical, can do, turns out that opens a whole wide range of different types of operational paradigms where you basically cut the tether and operate your vehicle close to infrastructure where you have power and comms. Or you don't bother to dock. You dump your data via that optical link. So there's a set of very promising things there. And then there's the microfiber, which is really Navy technology. For all I know, somebody in this room might have even developed it, really developed for torpedoes. We use it for deep ocean systems. So we use it to get down to the deepest part of the ocean, to the Challenger Deep, and we use it to get under permanent ice shelves. So if you take a look at some of the capabilities there, if you look at the acoustic comms, this kind of started out really in the 90s at Woods Hole, if you kind of look at a Woods Hole sort of centric perspective of this. And if you all know Art Baggerer, MIT professor, joint program professor at Woods Hole, emeritus now, really played a very large role in this, and as did a number of his students. So he developed that core technology, which then started being, in effect, coming together with these new small, low-cost vehicles. That's actually one of my old Odysseys there, with a couple of the acoustic comms folks behind it. And then we started using it, and of course, by the mid-90s, they were beginning to integrate them on real Navy submarines, and then, of course, into the more modern AUVs, sort of the Mark 18 Mod 1s and so on, a variety of different programs that probably you all know about. Now, the milestones for the optical comms, conversely, is a lot more recent. So it's more like 2006 or something like that. Norm Farr, who is really the leader for this effort at Woods Hole, actually came to Woods Hole from the medical surgery background. So he's a guy who really did really high power lasers, and he always corrects me. It's not for cutting flesh, it's for ablating flesh. So got it. So, but nonetheless, this is somebody who really intimately understands lasers. users, understands how to couple energy into fibers, and became, in effect, the advocate for developing this set of optical comm systems in the ocean. And, they went through a series of things, and actually, to a large degree, this was really motivated by the development of the ocean observatories in ocean sciences, where we've begun, the ocean sciences is sort of at the tail end of one of the biggest installation infrastructure projects in our history in this country. A significant fraction of $1 billion, and part of it is running cables out in the Pacific Northwest, out of Washington State, out to the Juan de Fuca Ridge, out to places where there's volcanism basically every day. And that gives you this opportunity to connect to instrumentation, maybe put a docked AUV out there and so on. And this optical comms to us seemed like a really great way to be able to talk to instruments that was in the vicinity of such a network system, but maybe wasn't plugged in, because plugging in requires you take your ROV down. So as a consequence, communications for observatories has really gotten to be a big thing. That one in the upper left, I couldn't resist putting that in. I actually wrote that proposal when I was back at Mbari. That was our testbed observatory out of Monterey Bay, 900 meters for developing, in effect, a lot of the instrumentation and operational methods for the scientific cabled observatories. And then you can see on the right, there's been an awful lot of work in the Arctic. And of course, if you run vehicles in the Arctic, you all know it's a little bit like, you got to get the vehicle back to the ice hole. If you don't get the vehicle back to the ice hole, it's potentially quite embarrassing, because you're probably going to end up going around digging holes in the ice, and you can't do that too surreptitiously. All of the other PIs in the ice camp will surely notice. So you really work hard to get that thing back to the ice hole and docked with whatever structure you have down there. And there's been some really great work in long endurance vehicles under ice. So the other thing that happens, of course, is that when you have these comms capabilities, if you think of it as a system, as opposed to thinking of the vehicle as the vehicle, if you think of you're designing an observation system, you begin to realize that your conception of what is a vehicle changes. And in particular, there was this great interest in returning to the deepest part of the ocean, 11 kilometers some years ago. And as that engineering challenge took form, we realized that the cables that we were using for our ROVs were just too heavy. They wouldn't even support their weight at 11 kilometers. And there's a lot of stories about the Japanese actually building a system where they try to get around this. But we basically decided that we would eliminate, I say that's really Andy Bowen's project, decided they'd get rid of the heavy part of the cable, which is the copper. So don't transmit power to the vehicle. However, keep the fiber. Well, if all you're doing is keeping the fiber, then you don't need all the strength member. And you suddenly go from a cable that's, the size of a garden hose down to something which is the size of your hair. Well, a little bigger than that, but it's pretty small. And now you can run down to the deepest part of the ocean, in effect, with a system with a cable pack which is this big, as opposed to something which you actually have to ship with a number of different shipping vans, in which you have to actually operate, for a normal ROV, you have to operate off a ship with DP, because cable management includes management of the top point of that cable. It's a critical piece of it. So you start going to these light fibers, and you suddenly can run an 11-kilometer rated vehicle off of a fishing boat. Pretty cool. And that actually led to a whole set of different types of platforms. You can now begin to combine these various type of, you can have a light fiber to a system which is temporary, because that light fiber might break. So that vehicle I showed you has to be capable of being an autonomous underwater vehicle when the cable breaks. But while the cable's not breaking, you can run it like an ROV, and you can pick up samples, and you get the full video experience like you do with a scientific ROV. And if you're diving under a permanent ice sheet, this lets you do things you simply can't do with autonomy in this day and age. Now, there's other classes of vehicles as well. These are pictures of a couple of vehicles that I designed. The one in the back there is a Dorado. Started development on that at MIT, finished it at Mbari. It was licensed to Bluefin, so it's kind of the basis of a number of the Bluefin vehicle designs. And then the vehicle in the front isn't commercial yet. That's a Tethys vehicle, and it's kind of the last vehicle I built. Now, the vehicle in the back, there was a section that we built for that, which was a semi-fuel cell section. And when that semi-fuel cell section was inserted, that vehicle could run 1,500 kilometers, theoretically. I say theoretically because that semi-fuel cell also had a catastrophic accident. Fortunately, no one hurt. The vehicle was in the water at the time, so we never actually ran it, that 1,500 kilometers. And I think, again, those of you who run with these, use these energy systems in vehicles, probably like I, have a healthy fear of them and a strong desire to make sure that they'll work. That vehicle in the front runs 1,800 kilometers, almost as far as the vehicle in the back. Designed 12 years later, something like that. And a large part of the difference just has to do with the fact that the vehicle in the front, we really focused on energy efficiency. We have focused on making the most efficient propulsion system, the lowest drag vehicle, the lowest power electronics that we could. And we ended up having a vehicle that could run for something on the order of 3 weeks at sea. And that particular vehicle, the way you operated it was operated actually via your cell phone. So it would pop up, it would send a message to the server, and you'd get an email or however you chose to get it. If you were on watch, you would get a notification that the vehicle was on the surface and everything was okay, or everything wasn't okay and you should do something. Latter didn't happen so much, but does happen. And one of the big lessons of that vehicle is reliability. Actually, you can get around an enormous number of problems with a very small bandwidth pipe. It used actually a iridium, 1200 baud iridium link. Now, when you start building these smaller vehicles, one of the questions you ask, and I kind of have this a little bit out of order because actually we asked these questions really the other way around, but the question really is, why use just one? Those pictures on the left show a notional survey where you have a vehicle that's mowing the lawn. Now, I think like many of the oceanographic surveys, we're measuring a time-changing phenomena. We have a certain amount of time in which we have to get the survey done. If we don't have it done in that period, the phenomena changes, and we're not changing the same, we're not measuring the same phenomena anymore. Now, the thing is that if you look at the energy consumption equations for these vehicles, there's really two very simple terms. One doesn't depend on velocity at all. It's just the hotel load of the vehicle, so it's the power burned by all the computers and things like that. And the other is the amount of power you use to push the vehicle through the water. And it turns out that amount of power goes as velocity to the third power. So every time you double the velocity of the vehicle, you increase the power consumption by a factor of 8. It's a very painful trade-off. Now, the interesting thing is if you put two vehicles in and try to accomplish the same survey, what you find is, of course, those vehicles can travel half the distance and still accomplish it in the same amount of time. That means they're traveling half the speed. That means they're each using 1/8 the propulsion power, and a lot of times the vehicles are propulsion limited. And as a consequence, you actually can end up building a system that uses 1/4 the energy by using two vehicles instead of one, provided you can keep your hotel loads low. Now, you're probably saying, oh, okay, but I didn't throw the power consumed by all of those other sensors in there. And that's true. I pulled a little bit of a fast one there. On the other hand, I didn't allow myself to reduce the vehicle size, because that's the other thing that happens. Because as you allow yourself to reduce the energy consumed by the vehicle, your vehicle size gets smaller. And what that does is that reduces the drag. And so as the drag reduces, you in turn are using less energy, and the vehicle size gets smaller again. And that's what's shown in that graph there on the right. The blue line shows a survey, so a notional survey, which takes you, which is accomplished in a survey rate of 1 by a vehicle of weight 1. If you look at how much it requires, how big your vehicle has to be in order to accomplish that single vehicle, the survey at 5 times the speed, that propulsion power consumption drives you up to a vehicle that weighs 1,000 times as much. So it's a very, again, so Mother Nature was not kind to us when she put together the drag equation. So on the other hand, let's take a look at the two-vehicle curve, which is that orangish curve. And what you can see is it sort of peaks out a little bit more than twice the rate. What's more, its weight there is a little bit less than the one vehicle. And that's not because I'm only calculating the weight of one vehicle. That's both vehicles put together. If you look at four vehicles, it's a little bit less again, right? And the survey rate's now almost up at 6 times what the first vehicle was. So what's going on there? Well, what's going on there is a couple of things. You're in that virtuous cycle where you're reducing the vehicle size as you're reducing the weight. And that's allowing you to make very small vehicles. Now, the small vehicles actually have an optimum speed which is higher than the bigger vehicles. So your optimum survey rate actually goes up. So this is the thing. For distributed systems in the ocean environment, if you want to cover a large amount of rate in a short period of time, and this is something we kind of realized in the ocean sciences back in the 90s, what you want is you want a lot of small vehicles, and you really want to focus on payload. And so if you can hit play on this one here, this is actually a field program that was run in 2003 after we went through and developed all the gliders and various AUV systems. We carried out this experiment off the West Coast. So there's a coastal environment. You're looking at sea surface temperature. It's an upwelling system. So that blue water there is fresh upwelled water on the surface. And then down under the water, there's all of these vehicles. So these are mostly glider vehicles, so these buoyancy-driven systems. Back for that particular experiment, we had some crazy ideas about them working in teams. That turned out not to work so well. But it was an idea that we tried out in that particular experiment. And then we were using aircraft and ships and drifters as well. And so here you can see that propeller-driven vehicle swimming by, and then a little while later we have our glider. Now these vehicles aren't operating in a vacuum. What's happening is they're actually telemetering all of their data back to shore. Why is that? Because the real point of this whole thing is to build sort of an underwater equivalent of a weather system. So all of that data goes back to shore, where those shoreside servers then disperse it to actually, in this case, 3 different research groups, to Jet Propulsion Lab, to Harvard, and to the Naval Research Laboratory, who then run those predictive models and tell us where to send the vehicles next. So that was in 2001, and believe me, we all thought it was a miracle when everything actually worked, and we managed to keep 10 vehicles in the ocean for about a month. But as I said, these days, physical oceanographers pretty much do this all the time. So let's talk about smarter robots, because actually those robots there weren't really very smart and didn't have to be very smart. So autonomy, and I'm going to give you, there's a lot of different definitions of autonomy, and I know that we could probably get a great food fight going here if we had a discussion about definitions of that particular word. And I'm going to give you kind of my simple-minded breakdown of it. I think of autonomy as having sort of 3 elements. First of all, autonomy is sort of the ability of the vehicle to function independently, right? But right at the top there, I put mission configuration, because an autonomous system might be autonomous while it's out operating, but certainly one of the most challenging things is for the human operator to tell it what you want it to do. And the more sophisticated the vehicle, the harder it is to do that. And particularly as you get into fault diagnostics, you start coming up with almost a factorial number of complications that you're trying to manage. So mission configuration is a really central and important part of autonomy. And by the way, the part that we're probably the worst at. Perception is another piece that the robotics community really greatly underestimated for a very long time. I think most people in robotics and in AI kind of thought all of the action was down there in the lower left-hand corner, in the decision-making part of it. But decision-making is impossible, right, if you don't have any information about the environment that you're operating in and you don't know what the human operator wants you to accomplish. So in fact, the perception protection piece of this is something which today I would say that a lot of what's going on, a lot of the excitement in robotics really doesn't come so much from advances in decision making. It comes from the fact that our sensors are better and our perceptive capabilities, our software for interpreting that sensor data is much, much better, and we're able to extract it and say, yes, that is a can on the table there, not a bunch of pixels. We can have a sensor that does that, and that makes the decision making that much easier. So I think that machine learning and unsupervised machine learning, we have a fellow at our organization who's doing some great work there, Yogi Girdhar. It's light years ahead of where I thought it was going to be. If you had asked me back in 2005 what I thought the capabilities would be, I would have never have guessed we would have covered as much distance so fast. Now, I think the other piece of this really revolves around the fact that what do these vehicles produce? They produce data, lots of data. And after that 2003 experiment, for which I was the overall PI of, by the way, at the end of that, things had kind of worked. So the O&R program manager said, you know, I'll give you one chance. You know, what's your wish? What project do you want to work on? And I said, well, I think really what held us back was data management. I think if I'd put 4 more vehicles in the water, we wouldn't have been able to deal with the data and we wouldn't have been able to use them effectively. And so I started working on data management for ocean systems, and I find it a fascinating area. I connected with this guy who was up the road in San Francisco at the time, Jim Gray, and Jim had this vision of data science, e-science, which I found very attractive. So he actually worked with Microsoft Research at the time. Jim was a Turing Award winner. He had one of the people who had created the relational database, which is behind, I guess, every transaction we make at an ATM machine. So Jim's view of the evolution of science, and this is an engineer's view of science, because Jim is very much an engineer, was that it started out as sort of the empirical observation and recording of natural phenomena. It was an empirical science. So, you know, we tracked the motion of objects in the heavens and wrote them down. And then a little while later, several thousand years, I guess, began to develop equations for turning the observations into theories which had some predictive skill. And so this theoretical branch of science is really, I think, what most of us think of when we think of science today. Now, his point was that, of course, you know, particularly in physics, my old discipline, there's very few things which you can solve analytically in the world. Almost everything that we interact with is much more complicated, and you can think of the weather and ocean prediction as being examples of that. And the way we work with those types of systems, of course, is we developed a computational branch of science where we take all of the laws that we think we understand very well, and then we solve them computationally within a computer environment. And when I was going to grad school, I can remember I actually got a lot of points because, you know, I was one of these younger folks in the physics department, and I knew how to do that, right? A lot of the older PIs, a lot of the older scientists actually weren't that comfortable with this new computational branch of science. Now today, Jim would argue, and Jim actually was lost at sea, so he disappeared at sea on a sailing trip, so he's no longer with us. But what he would say is that we're in this data exploration phase. So we're in a world where we've instrumented the world, and you know, in the ocean environment, it was a little hard for me to get my head around that because we're always data poor. But you can see it coming, right? The sensors are cheap. The ability to get the data back is getting easier and easier. And so increasingly you find yourself with observations that you didn't plan scientifically. It wasn't part of an experiment that you put together. It wasn't an answer to a hypothesis. It's just a description of the world in an almost bewildering amount of data. And now the problem becomes sifting through that data and inferring what it tells you. And this is, I think, in effect, in the ocean environment, what the robots enable. They enable this e-science, this data exploration of the ocean environment, where we begin to observe the ocean to a degree that we've never been able to in the past. And it is, in effect, transforming many of our sciences into a data science activity. So I think here I'm sort of closing on the end. I'll just say that I think no big surprise. I've alluded to it a number of times through the talk here, but these robotic systems, of course, have enormous applications in the defense world, but they're really enabling industries, and you could see that in oil and gas. Currently, the offshore wind folks are beginning to really pay attention to how do you survey, how do you inspect, how do you maintain their infrastructure. Cabled systems have been there for a while. There's a set of threats to cabled systems which are a lot more modern, due to some degree to the fact that the robotic systems are so much more available. One of the couple of meetings that I've held up at HUI, some Department of Energy folks showed up, and they showed up because they're interested in growing algae in the sea. In their case, macroalgae. This picture is of microalgae. And then aquaculture. Aquaculture is when I talk to folks, the people who are the most excited about it are the financial folks, because they see a world where the developing world is getting wealthier and wealthier, and the thing that they ask for most is improved diet. They want protein, they want meat. And it turns out you can't really satisfy that demand from the terrestrial environment. And wild fisheries are already under stress, and many of them are collapsing. So what you end up turning to is aquaculture. You end up sort of moving from the hunter-gatherer stage to the farming stage in the ocean. And you need to do that offshore in some pretty harsh environments where aquaculture doesn't work now, which turns it to some degree back into a robotics problem. So I see here this nucleus of a robotics community in the New England area. So if I were to draw a triangle there from Boston down to the Cape and then maybe across into Connecticut, you'd encompass a fair number of the marine robotics elements of this group. And if you live to the north of my triangle or outside my triangle, I apologize, but not trying to be exclusionary. I'm just saying that we actually have a critical mass here of the right ingredients to be major players in this new and emerging market. Now, I think the other thing that we all recognize is that in order to get there from here, it's going to take a lot of funds, and it's going to take a particular kind of money. And I think that's part of why it's playing out here and not so much on the West Coast. And I spent 15 years out there in Silicon Valley. Fantastic, innovative, tremendous place. But they want answers fast, right? This requires a bit more patient money. It takes a longer perspective on things, and I think that actually fits to some degree with this part of the country. So I have one last video here. It's a bonus. This is an AUV, and it has to do with sort of surprise in the ocean. We tend to put our cameras looking forward in our vehicles, not looking back. Amy Kukulias put her camera looking back on a vehicle, and when they took the vehicle out of the water, they were astonished to see that apparently a whole school of fish had decided this. I don't know what it had decided, but it decided to follow this vehicle. I always say it decided it was their mama, or maybe it decided this vehicle was going to protect them from predators. But the point is that if you looked at the camera out the front of the vehicle, you wouldn't have seen anything. It took a little bit of hindsight to figure out that there was a surprise there. Okay, yes. And on that note, I probably should end. So thank you. Questions? Yeah. So be happy to take a couple questions here. Go for it. I was about to pick someone at random.
Jim, great presentation. Can you talk about based on your curves that you had earlier, the trade-off between autonomy, artificial intelligence or whatever, and data communications in light of things from a defense perspective, where you might be in as the Admiral said earlier, not necessarily an A2AD environment, but a contested environment. Has research, what's the research looking like with regards to multiple vehicles in the area where you have a denied environment? Communication, comms might be denied,
yeah,
but autonomy, and you still have to get the mission accomplished.
Yeah, so I think, well, I'll tell you quite frankly, it's an enormous challenge. Now, those long fibers How long are you going to run them? Where are you going to run them? How long are they going to last? You could see yourself sort of attempting to put some sort of hopping infrastructure together that might function as a network, that might provide you sort of a network windows, if you will, through the environment. But I think that you know, one of the challenges that I see really revolves around the fact that for some of these missions, we're really looking for cooperative behavior between vehicles. And cooperation really requires communication. And so I think, in particular, it requires a common operational picture. And so one of the things that we've been focusing on is how can you provide that common operational picture at sort of lower bandwidth, so that when you do your communicating and you say, okay, bad guys over here, that's kind of a low bandwidth message, right? All of the high bandwidth stuff of the current fields look like this, the oceanographic field looks like this, and all of that high bandwidth stuff, right, already is kind of dealt with. And so there's a fellow, actually an old postdoc of mine, Sergei Frolov, who's currently at the Naval Research Lab, who's been working on what we called compact models there. And so that piece of the puzzle is I think one that really will offer some pretty tremendous returns. So these have to do, so if you run a normal oceanographic model, and let's just sort of say it requires 1 million cycles for a particular activity, some of these compact models can actually give you a predictive skill because they're trained by the big models for the environment you're operating in, trained both in terms of the variability to expect using principal component analysis, and trained in terms of understanding what the progression of principal component ensembles to expect in that environment. Now, it turns out to give you pretty surprising predictive skill for short periods, and a very efficient way of communicating not only instantaneous fields, but fields that can then be propagated in time between platforms. So I think that, you know, on the environmental part of it, which of course is where Woods Hole focuses on, we see this a little bit like almost everything else we do underwater. There is no silver bullet. You know, there's no one thing that is going to be our solution for communication in that environment. But we're going to have to build up a toolkit, which is going to involve a bunch of different types of communication modalities that we might have, some of which are really high bandwidth, but very perishable, other of which might be lower bandwidth and maybe only functional in certain times, maybe even of the day, depending on the acoustic environment, but they're generally available. And then there's got to be a set of methods for information management. How do you provide exactly the information that's needed to that particular platform or back to the human operator, and how do you maintain a common operational picture across the platforms? I think that's kind of one of the more challenging ones. So, sorry, lots of words, not a good answer, tough problem. Yep.
So along those lines, Jim, the panel before here talked about unmanned systems, and Secretary Kelly talked about the challenges. One was the comms, but there was, you know, the precision timing, energy, biofouling, all of that. Could you just talk in general about the industry, government, academic approach to solving all these problems kind of as a consortium as opposed to individually?
Oh, yeah, great. So that topic near and dear to my heart. So I'm a big believer that it, you know, really takes all different types of organizations. You know, I think, you know, the universities, the MITs, the UMass, the Northeasterns, the URIs, you know, these are organizations where you have a lot of students, super smart faculty, and a lot of opportunity to experiment. Now, you're not going to turn anything into a real product or, you know, build actual oceanographic systems. There's exceptions to that, but for the most part, not. But I think that there's this real innovative ecosystem that we need to nurture, right, and connect to practical problems in the academic environment. And I think they're hungry for it. I mean, when I go to MIT, they are looking for an excuse to start a company, right? That's what they want to do, and they're looking for a problem that they can solve. And so, you know, I remember at our last we have an entrepreneurs forum we hold at Woods Hole for the marine robotics community every summer. At the last one we had this aluminum power system, which is an MIT spinoff. So I think there's and the beautiful thing is those people, right? You know, because you don't transfer technology by sending papers, you transfer technology by sending people, right? And the beauty of the academic system is the knowledge is mobile. Right? It'll go to the organization which values it the most. So I think there's great opportunity there. In the research institutions like Woods Hole, you know, we've kind of carved a niche for ourselves, particularly if you take a look at the Remus group, where we have a group of individuals who can talk with the advanced robotics folks on one side. So I'm a editor on science robotics, for example, so I get to see a lot of the cutting edge research, as does my colleague Dana and my other colleagues at Woods Hole. At the same time, Dana goes to sea and he takes his systems and he'll operate them in the toughest environments on the planet. And so he really understands what works and what doesn't work. And so he has an ability to look at sort of some of these crazy ideas and sort of see when they offer an opportunity, I think, a bit early. Now, I think, again, you know, from a Woods Hole perspective, we're not going to, you know, we're spin a company out, sure, but license stuff, absolutely. So I think for us, you know, we're looking to that innovative ecosystem around us, which consists of everything from big companies to very large companies, depending on the scale of the enterprise. And ultimately, the big companies, I think, in the defense world, you know, have the access, the clearances, and the insights sometimes to really connect it to problems that for the average small company are simply not visible. That market expertise, by the way, is the thing that the little companies really suffer for. Usually technically really smart, willing to work around the clock, but don't really know the market domain. And so that's something that we try to help them with. Don't actually always understand the finances that well either. And then, of course, the warfare center. So you know, I think, you know, how do you connect to the Navy? How do you get this stuff out there and in the fleet as quickly as possible? And, you know, we've got a submarine base over in New London. We've got the Naval Undersea Warfare Center. We are sitting in a place where we've got a number of the organizations that are connected exactly to the people who we want to help, and they're right here. And they're very happy to talk to us. We go over to New London and visit them, and they love to see us, and we invite them over, and they crawl inside Alvin and won't come out. So I think we have a great environment here, and opportunities to bring the community together like this are really central to building that. And a lot of it has to do, I think, though, with sort of a mutual respect between these very different organizations that often have a different set of priorities and don't always understand the value that the other entities are bringing to the table. So I think it's something that we can all work to break those barriers down. So thanks for the question.
All right, Jim.
Well, great.
Yeah, thank you very much, Jim. Before you go, first I want to thank Jim for braving the traffic that took several hours for you to get here. It's certainly well worth it for me and hopefully all of you. I think what you mentioned, Jim, is absolutely spot on. It's really collaborating across this great community that we have here between academia, government, and industry. I think our partnership with Woods Hole is really illustrative of that. Appreciate you coming all the way down here, and as a token of our appreciation, we'll give you a now famous SENEDIA coin.
Oh, wow, great.
Thank you very much.